So I hope everyone can hear me, and let me turn on the video so that everyone can see me as well. So I'm going to talk about gravitational waves in 3 lectures. I think you have already had an overview of gravitational waves. But then what we are going to do, since many gravitational wave lectures you have heard so far, but then some people, and then some people did not hear anything. So what I can do is that this will be a small experiment that I will talk for say 10 to 15 minutes, and then we'll have a small interaction. You can ask your questions on the chat box. Chat will be enabled, and then I can take a couple of questions and then move forward. Okay, so if you can, so just to test, maybe 1 or 2 of you just put a chat message here so that I can see whatever you are writing. And if you have to ask a question after the session, let's say when I'm speaking, you should better good, I can see it already. So it's chat is working. Now what you should do when I'm speaking and you want to ask a question, then you put it in the chat box. Otherwise, you can wait for me to pause. At that point, you raise your hand, and then I will take your questions. Okay. Let me just put this thing also on so that I can see who all are asking questions. Okay. Now, yesterday in West Bengal, of course, there was a huge cyclone, and that has basically disabled a lot of communication. So I guess many people would be finding it difficult to connect via internet. There is no internet right now, I think. I mean, only in few cases there is internet, and many people are still suffering. But anyway, so in the next lecture, if there are more people coming up, then I can briefly summarize. If you meet your friends who could not, if your friends from that region communicates with you that what happened in this class, then they can of course contact me later. Okay, let me get started. So these lectures will have basically broadly in 3 lectures I'm going to cover: origin and sources, then detection, and the future. Now, it does not mean that it will be restricted to each. I mean, this boundary is going to be sort of fuzzy, but this will sort of give you an idea how to the orientation of the lecture. Okay, now this is not yet. So just to begin, you know that of the gravitational wave astronomy essentially started with this picture, and probably a lot of you have seen this picture. This is the schematic diagram of the first detection. Okay, 2 compact binaries merged. So they were going around each other, they were inspiraling, then they merged, and then they formed a bigger black hole. So this is the basic idea. We will know more details about this detection later on, but let me just give me a minute to pause. Somebody give. Okay, so and this, what you see below, that red and blue, are basically the signals which were detected in 2 detectors which are 3,000 kilometers away, and they match the predictions of general relativity, which basically means that the probability that this signal was generated by anything other than the merger of 2 black holes is extremely small. It is basically 1 in thousands of years, that small. So this was the first detection. So why am I starting with this? The important thing here is to understand, and then of course, uh, 3 people got Nobel Prize for this detection, right? In 2007, Ray Weiss, Barry Barish, and Kip Thorne. I think many of you have heard this also. The important point here is that, of course, many people contributed to this. It was one of the biggest collaboration where people worked together and made a big discovery. And in this, and you can imagine in this situation which we are going through, this is also a good example that a lot of things can be done remotely over internet and so on. Okay, now the point here is that this is like we are in a situation which is like Galileo's first observation of the planets. I will show more about it, but this observation, of course, you have heard about this, that this is basically the discovery of gravitational waves, black holes, and black hole binary, etc. But the most important point is that this is the beginning of a new field of astronomy. Astronomy has the electromagnetic astronomy has progressed enormously in the next 400 years, and I will talk maybe briefly about this in the last lecture. But you can, from this picture, you can see that this is the Galileo's telescope. On the, I hope you can see my mouse pointer. And then there are many other telescopes with cutting edge technology which have given us, told us a lot about the universe. So, especially for the young student, the message here is that this field has just started and there is a very long way to go. So, and also the thing is that whatever, so if you see sort of the history of science, what people were thinking at that time when Galileo discovered, and what people think now about how astronomy is, it is quite dramatically different. It started from the Earth being the center of the universe and everything going around it. Today, of course, this question is just not there. But even lately, even like 100 years ago, people were thinking whether the Milky Way is the universe or there are other galaxies outside the universe and things like that. There are dramatic changes, whether the universe is expanding and so on. So the point here is that right now, what we are thinking would be the gravitational sources are based on our current understanding. And of course, we have detected the binaries. That is a clear proof that our understanding is not completely wrong. But there can be much more beyond it, which we cannot even we cannot even imagine at this point. Okay, things will become clearer probably maybe 10, 20, or 100 years later. Okay, now let me come to the main content. I understand that you already have the general relativity lectures and you know what it is. But just to summarize in one slide, general relativity, and I will also connect it to gravitational waves. This picture will become easier. Basically, general relativity gives a geometric picture of gravitation. So basically, the equivalence principle can be translated to a geometric picture because you know that the motion of massive particles are independent of their of the material or the mass. So you can essentially do sort of like ray tracing in geometric optics as long as the test mass is small. But things get more complicated when the test mass becomes large. So I will come to that. Now, general relativity also predicts black holes and gravitational waves, and that will be the primary content of this talk. And again, this one-line summary, which you may already have heard, but this will be useful for what I'm going to say a little later. that space-time tells matter how to move, and matter tells space-time how to curve. This is what Wheeler said in one line, that this is what general relativity is. So, okay, before going to this slide, do you have any question? I will pause here for a little bit. If you have any questions, then ask. Otherwise, we will move. So far, we have not gone into much technical details, but still I want to check. Okay, I guess there is no question at this point. Let us move on. So, you know that general relativity, the set of equations which determines the motion of mass and energy in general relativity is given by Einstein's equation. Here we are considering just a simple Einstein's equation without any other terms. The left hand side, this G mu nu describes geometry. The right hand side, T mu nu, describes the dynamics of mass and energy. Now, and when we solve this equation, we get the full dynamics of how the systems are going to evolve. So basically, T mu nu captures the energy, momentum, flux, okay, and G mu nu captures, as I said, geometry. But both are, in some sense, conserved quantities. That their divergence is zero. Now, what we do is that, which you probably have not yet, which was probably not covered yet, was that there is this quantity small g mu nu, the metric, which essentially tells us the distance between 2 points in a on a curved surface, can be broken in two parts. One is flat, that eta mu nu, and the other part, small h mu nu, when the surface is nearly flat and there are only small perturbations on the surface. Okay, this is generally true, but we will work in the 3+1 dimensions, which is a basically 4-dimensional hypersurface, and there also this holds. But the interesting part is that okay, in 3+1 dimension, this eta mu nu becomes the Minkowski metric. Okay, so which probably you have seen in special relativity. The interesting part is that when you do a break the g mu nu in this kind of form, the h mu nu part, this perturbation, acts like a okay, there is a question. I'll come to that question very soon. Acts like a field on a flat background. So you can treat this h mu nu as if it's an independent field instead of always carrying it around with g mu nu. The question is that why C is not set 1 as we do for other purposes as natural units in Einstein's equation. Yeah, you can put C equal to 1 units, doesn't matter. The thing is that it becomes easier if you put C equal to 1 to look at the equation. It becomes difficult to convert back the equations, the results, when you want them in normal, understandable units. So it's just a personal choice what you want to put. But if I did not put this term, for example, that C is equal to 1, what would see if I put C equal to 1, what would have happened is that you would not see this scaling. So how weak the coupling is between the geometry and mass would not be evident. So here, if you can see that G is already a small number and C to the power 4 is also a very small number. So this thing basically means that the effect on G mu nu is going to be small. Okay, so I will not, so there is another question on whether the gravitational constant is really a constant, but that is not part of this discussion. But so far there is no evidence that gravitational, that the constant G, which is the universal constant of gravitation, is varying. But there are many tests which goes on. Science, we cannot say that it does not vary. We can only say that so far there is no evidence that it is varying. Okay, now coming back, so what we can do is substitute this small g mu nu in Einstein's equation, and on the to the left hand side, and do a lot of algebra, and then finally you come to a point that you will get this left hand side as this box of h mu nu bar. H mu nu bar is basically a trace reversed h mu nu. The thing is that we cannot get into this algebra in this course. I mean, it's too small to basically. Most of you are not even familiar with general relativity calculation, so we cannot do this whole algebra here. But the analogy I can give is very clear. Will be clear to you that it is very much like solving Maxwell's equation. When you put Maxwell's equation, or when you try to get the wave equation in Maxwell's equation by taking the curl of curl and things like that, you finally end up getting something like box of some quantity equal to a source term, which is often denoted as J nu. But here it is a tensor instead of a vector. So that is exactly what is happening. Of course, in you can go to a F mu nu formalism also. Anyway, so basically the point is that this equation is equivalent or similar to the equation which we get in electromagnetic theory. And therefore, the solution, the way we solve this equation is also going to be very similar. We use Green's function and to solve this. Okay. Okay, let me see. There are some more questions, and I will check what are these. C is the speed of light, right? How can we put the value of C is 1? Okay, so this you can, this is not very difficult. You can always choose a unit. So let's say that, one of us, let's say my height is like 1.75 meter, I think. I can call, okay, let us, instead of meter, I will use a unit called Mitra, which would say 1.75 meter is 1 meter. Okay, so these things are always possible. So, and then you can write everything in that unit. Similarly, you can do C equal to 1 redefine the unit so that C becomes 1 in a certain unit, but then you have to bring it back to the normal kilometer, meter, MKs or SI system. So that's the part, but that you can read outside this lecture. Okay, another question is that in the linearized gravity equation, does this lead us to assure that space-time curvature to be a 2D carpet-like structure? I will come to this. This equation is this equation is actually valid in little more general situations where the background need not be just flat, it can be curved and still there can be a perturbation. So you can always write the equations in that way also. But here, I mean, this is just a simple expansion, a perturbative expansion. Okay, so now when the source term here, that is this T mu nu, is 0, that is, let's say we are in vacuum, then what you get is an equation that box of this H mu nu bar is equal to 0. In that situation, like in electromagnetic theory, you choose a certain coordinate system or gauge in order to simplify the equations. Here also we can choose a gauge that is basically a coordinate system in such a way that that H mu nu has minimum number of non-zero terms. When you do this, it turns out that the solution for this H mu nu basically has only two independent components, which are written as H plus and H cross. See, this matrix has 4 non-zero terms, 2 are H plus and 2 are H cross. That means there are basically 2 independent components here. Also, you see that there is this term omega t minus kz. That comes quite naturally because we are solving an equation which is of the form box h mu nu equal to 0, this box basically has an operator. Basically, it's like del square del x square plus del square del y square minus 1 by c square del t square kind of a form. Okay, so when you solve an equation of that form, that differential operator acting on something equal to 0, the solution will always be of this form, k dot x minus omega t equal to constant. So basically the constant phase surfaces will lie on that. If the propagation direction is in the z direction, z axis, then you can write it this way, omega t minus kz. Okay, basically the solution will be of that will be the only independent variable to describe propagation. Now it turns out that, so this equation followed from general relativity. There are other theories of gravitation and so on, but in general relativity, this equation basically means, because you are getting a box h mu equal to 0, and that box has a term which is 1 by c square del t square, and that c is the velocity of light in vacuum. It is this c which is coming. It means that the velocity of gravitational waves is going to be c. Okay. Now, okay, I will come to the questions in a minute, but the point here is that one last point here is that since there are two independent components, and you can always write this equation, if you split this matrix in two, one will have only h plus, one will have only h cross. So you will write the thing as this solution as h plus times a matrix plus h cross times a matrix, and you see that both these two matrices or tensors will have all zeros except two. In one there will be two ones, okay, in the diagonal term there will be 1 and minus 1, so this is of course stress field. In the other one there will be two ones along the other diagonal. That is, I think you can understand where it is going to be. So basically those two represent two polarization states of gravitational waves. Okay, now I will come to the questions. Why do we have to do? We don't have to do linearized gravity. It is just going to be too complicated if you use linearized gravity. Okay, by the way, I would say that you ask the questions to everyone, so that I think you can do that by choosing this menu, so that you can, other people can also see your question. The h plus and h cross are constants? No, they are not constants. They are, so in electromagnetic theory, you can always write the electric field, let's say propagating electric field, which is transverse. Let's say the wave is propagating along the z direction. You could always write there is Ex and Ey, right? Ex I cap plus Ey j cap, where each of these Ex and Ey can be sinusoidal functions with different phase. That means both can have the same frequency omega, but can have different phase, and based on that, you will get different kinds of patterns. So these are those. So the question is that the matrix is symmetric. Does it convey any physical meaning by this? Well, the physical effects are going to be determined by the. I mean, these are coming from basically the inherent symmetry in Einstein's equations. So the effect of gravitational waves on matter will be determined by this shape. So we will come to that. The other question is that why we are choosing a transverse and traceless gauge. We can choose any other gauge also. That is not a. But the thing is that you want to choose a gauge where the solution becomes very minimalistic. That is often useful. Okay. All right. Okay. Let me see. There is no hand up. Also, I will just pause here a little bit, and I will also have to check whether. Oh, sorry. I will come back to this later on, whether there are other questions on YouTube Live. And oops. Other questions? Okay. Okay, so there are questions on there are questions on YouTube Live also for the YouTube Live viewers, which will become clearer as we go along in the probably in the next lecture or later in this maybe later in this lecture. So I will come back to those later on. Okay. Any other? Okay. What is a gauge? Okay. This you can. Okay. Let me. You can certainly find it out. If you are in, let's say, in higher level physics, then you will certainly encounter what a gauge is. It's a coordinate choice. Basically, you choose the variables in such a way that your solutions become more useful to extract physics in a certain situation. Yeah, so there is another question is suggestion is that can I take questions at the end of the session? That I'll also do, but I will also take some questions in between, because otherwise people will forget the question, and then I have to explain many things in order to explain. For example, here that what is about restless, transverse restless gauge, and so on. Okay, now moving forward. Now, what are the properties of gravitational waves? These are transverse waves, like electromagnetic waves. Again, you will certainly encounter what a transverse wave in your course versus what is longitudinal. They travel at the speed of light. I already told you why. They have two polarization states. I again said why there are two. When you solve the Einstein's equation, you get that. They interact weakly with matter. Now, this is a crucial point, so I will spend some time here. The thing is that because they interact very weakly, it becomes extremely difficult to detect these waves. So let's say that when let me give you an example of what exactly happened in the first detection. There are two black holes. One was 36 solar mass, another was 29 solar mass. They went around each other and merged. The final black hole was 62 solar mass. That means 3 solar mass worth of energy was emitted in basically 0.2 seconds. That was the duration of the signal, 200 milliseconds. Now, if you compare that energy with, let's say, the electromagnetic energy, which we get from the sun has been shining for billions of years. And so far, sun has lost probably few percent of its mass. I don't know the exact number, but it should be of that order. Then, and that is enough to give us light, like create summer on the earth and so on. Now, if you compare that few percent of the sun was converted to energy over several billion years is good enough to give us so much energy, and it's very easy to detect the sun, of course. On the other hand, of course, sun is also close, but even then there are stars which are further away and we can see them. On the other hand, what we are comparing against is an event which lasted for only 0.2 seconds and consumed 3 suns. I mean, converted 3 suns to energy. So the energy release was enormous in the first detection. It's so many zeros you have to add after one in order to compare the fluxes, the solar flux versus this the energy flux from the binary merger. Yet it was so difficult to detect, and that is because gravitational waves interact very weakly with matter. And I think yesterday Sanjit Dhurandhar gave you examples. Now why? So that is why it took 100 years to detect them. But on the other hand, this is a very useful thing. Because gravitational waves interact very weakly with matter, they can come from regions which are otherwise dense and light cannot penetrate. Okay. For example, if in the galactic center there is a lot of dust and something is happening near the center of the galaxy, let's say 2 black holes are merging or 2 neutron stars are merging even, we may not be able to see them because of the dust. Certainly the dust is going to block it quite significantly. But on the other hand, with gravitational waves, since they don't interact that much with massive objects like dust, it can penetrate the region and come to us. A more interesting example would be about the early universe gravitational waves. So the earliest picture of the universe that we have at present is from the cosmic microwave background. There will be lectures on cosmic microwave background certainly. So before that, what happened is that the universe was so dense that photon could not travel in a straight path. That is, it is like that you are observing something, let's say a plant or something, and somebody puts some lot of smoke in between. Then the photons from that object which you are observing are still coming to you. Okay, let us take a good example like a sun. On a cloudy day, the sun is still there, and you know that in a cloudy day, the sunlight that you are getting are still from the photons from the sun. But you still cannot uniquely see the sun because the photons are not traveling in a straight line. They are scattering all the time with these particles in the cloud. That is why we cannot see the sun. Okay, it becomes optically thick. So the same thing happens for in the early universe. That photon cannot come to us in a straight path, so it becomes sort of scattered. So we cannot take a picture of the early universe. Only after the universe has cooled enough, the photons, basically electrons and protons combine to form neutral hydrogen, and the photons could travel in straight line, and that happened after about 4 lakh years. That's 3.8 lakh years after the universe. Okay, if we assume from the Big Bang. Now the point is that there is a phase in the Big Bang model where the universe has to expand extremely rapidly. It's called the phase of inflation, without which the current observations cannot be explained. And at that time also, there was a lot of gravitational waves produced. That is the model's predict. We have not observed that, and it's a big research activity going on across the world to observe those gravitational waves in different frequency bands. But that we can hope to observe those waves from the first second of the universe is because gravitational waves can penetrate dense regions. So the dense universe, very early universe, which was extremely dense, cannot stop gravitational waves from coming to us. And that is a big advantage. And there can be, as we learn more, not in this lecture, but with observations, we may find more and more such objects which would otherwise not be visible in electromagnetic waves, because the signal would not reach us. Okay, there are 2 more questions. Okay, one question is that does gravitational wave interact with dark matter? Okay, so this yeah, this is slightly aside, but yeah, it interacts with dark matter. Like there was a lecture, I think, on gravitational lensing. Gravitational waves can also be lensed, just like electromagnetic waves. Okay, basically, if there is a massive object and a gravitational wave is coming close, it will get bent. What is the relation between followed by so okay, that is a good question. So the question is that how does the intensity of gravitational wave fall with distance? Is it like electromagnetic waves where the fall off is as 1 by r square in energy? Is exactly the same. But many times we talk about the amplitude of gravitational waves because we are looking at coherent sources. We'll come to that later. There the fall off will be, because we are talking about amplitude, will be 1 by r. Like electric field will fall as 1 by r. Okay, what are the two polarization states of these waves? As I said, this is a plus and cross that comes out from the solution. Okay, black holes observe and in okay, I will come to this question that the very in few minutes. Can we detect gravitational waves using the time dilation effect? Okay, there are efforts going on, but we will not get into that today. What happened to the okay? What happens to gravitational waves when they interact with matter? We will come in the next lecture. Okay, so that first question I will come very soon. Now, let us first check some of the comparisons between gravitational waves and electromagnetic waves so that you can understand the basically the relation, so that it is these relations are not like very solid relations. These are basically kind of indicated so that you understand what is exactly is going on. Now, for both gravitational waves and electromagnetic waves, space is the medium. They travel in vacuum. The source of gravitational waves, now again I said that these are not solid comparisons, but these are very good indications that what exactly we mean when we talk, colloquially when we speak. So for electromagnetic waves, generally we are talking about incoherent superposition of emission from atoms and molecules. That is, that when you are looking at, for example, a light source, you don't know which atom has emitted a photon at what time, but you are looking at a collective sort of stochastic energy that is coming out from a certain region. For gravitational waves, that is also true, that there can be sources of gravitational waves which are stochastic. But what we are generally when we talk about binary mergers, we are talking about coherent sources where the phase can be traced. For normal light, we are not tracing the phase, but for gravitational waves, which we have detected so far, we are tracing the phase. That is the primary difference. It is like lasers where the phase can be traced. Then the resolution. Now, generally when we are talking about electromagnetic waves, okay, like a telescope we say, so we have a picture that a telescope will be maybe some object like few inch, 9-inch telescope, 14-inch telescope, or a radio telescope which is much bigger, but still you can point that telescope to a certain direction and then some wave is coming, the sort of the scale of the waves. It could be meter wave, like as big as meter wave. But when we are talking about gravitational waves, we are talking about extremely big wavelengths. Okay, it is true that there can be small wavelength gravitational waves also, but when we are talking about I mean, in general, when we are talking about it, we are basically meaning a large wavelength gravitational waves. Like the ones which were detected in LIGO have typically 100 Hz frequency. So now if you basically take 3 lakh kilometer and divide it by 100, you know that it can be thousands of kilometers would be the wavelength. Okay. So I will go to the last point and then come back to the other one, because this has the direct connection. So because the wavelengths of electromagnetic waves are small when we are doing electromagnetic astronomy, you can take a telescope and move around. You can point in this direction, that direction, etc. But for gravitational waves, since the wavelength can be thousands of kilometers, which we are probing right now, in fact, it could be even bigger in the future when the detectors improve, we cannot just, it is impossible for our detectors to be moved around. They are big detectors, okay. They have to be a few kilometers long, and then we amplify the wavelength by the arm length by different techniques, which we'll discuss in the next lecture. So it is effectively a much larger detector and cannot be moved around. But we can still determine the directionality of a source, by which I will discuss later on. Okay, so that's because lambda is much larger for gravitational waves, the frequency will be smaller. That is obvious. Now, for electromagnetic waves, they can be absorbed, scattered, and dispersed by matter very easily. That I already, and you know that very well, because we are seeing these slides right now, means that electromagnetic waves can be absorbed and scattered and dispersed very easily. That's what is happening. I think all these processes are happening. But for gravitational waves, it is a very difficult process. Even if you can put a binary, another binary in the gravitational waves field, it will absorb and re-emit little bit, but the coupling will be very small. Okay. Yeah, that's about it. I think I have covered everything. And also for the detection, I said that we are generally measuring amplitude. Okay, so now I will just pause here and go to this one. This is the last thing we will cover in detail, because these are the primary sources. Any other questions? Okay, let me see what are the questions here. What happens when gravity interact with material? Say, by gravitational waves, can we differentiate between a Schwarzschild and Kerr black hole? So a Schwarzschild black hole is one which is not spinning, and a Kerr black hole is one which is actually symmetric, spinning. So we can differentiate in the sense that, I will come to that question in a bit. First, I have to explain how to detect those ones. Do gravitational waves interfere with one another? Yes, they can. But the probability, so since we are looking at gravitational waves right now, which are very small durations, the ones which we can detect right now, there are more sources. The probability that two of those will happen exactly at the same time and with overlapping frequencies is very low. But if they were there, they would have interfered. And also the other thing is that when we talk about, let's say, stochastic background, etc., which I may briefly mention, when we are calculating their energy, the spectrum, etc., we are considering their interference. Basically, we write them as a Fourier expansion, which essentially takes care of interference. Oh, sorry. I'll first explain and then go to a video, otherwise it become too distracting. Now, the primary sources of gravitational waves are compact binary coalescence. So let me explain what exactly is happening here. Two compact objects, whenever they come close in the universe, it is very difficult to not to interact. So the objects basically start going around each other. Why they don't come and hit each other? Because you have to conserve angular momentum. So if you have some even small initial velocity, you just cannot get rid of that until you have some sort of dissipation. In fact, gravitational waves is one way to dissipate energy. So what happens is that they go around each other. If they did not emit any gravitational waves, they would go around each other forever. Nothing would have happened. But since general relativity predicts that they will radiate some energy, in order to compensate for that, they have to come a bit closer. As you know, like when in an atom and so on, if you release some energy, you have to come a bit close to the center so that the total binding energy can, so basically the potential energy can account for the loss. So then what happens is that if it comes closer, then they start spinning faster. The inner planets, you know, moves faster. This is Kepler's law. If they start moving faster, they start emitting more. I will come to the reason later on. And then what happens is that then the rate at which they come closer becomes even faster. So this is like a non-linear process. Earlier I used to spend some time to explain non-linear processes, but now in this corona epidemic, I think everyone knows what a non-linear process is. That more the number of contamination, higher the rate. That is the exponential growth. The same thing is happening here. Faster it is coming, the rate is becoming even faster to come closer to towards merger. So there is a non-linear increase in the energy emission. What happens then is that in the last few cycles, they emit enormous amount of energy, and at some point they touch and they form a final object which then sort of settles down by emitting some damped harmonic damped harmonic modes. Basically they are called ring down modes, and they become a stable black hole. The first part of this whole process, the in spiral part, when two objects are going around each other, can be sort of done analytically. You can start with a Newtonian Newton's law basically, and then do a calculation, but that will not be very accurate. So slowly you have to add more and more perturbative term in order to go closer to general relativity. These are called post-Newtonian approximations. Then the marginal part is simply too complicated to solve basically solve analytically. So you have to people do numerical relativity on large supercomputers to solve this part. The ring down part again can be done analytically, and the first and the last part, which could be done analytically, India had significant contribution in this modeling. There is some equation here which kind of indicates what kind of strain you expect from this. So the H I showed is sort of like an a proportional strain that comes from gravitational waves. That if there is an object and a gravitational wave strain is H, then the distance will increase by delta L, which will be proportional to that H. And that H, if you can put some numbers to see what sort of signal you expect from there, it is like 10 to the minus 21, which obviously is a very small number, right? And this is for, let's say, a solar mass black hole, or not black hole, I mean neutron star. And let's say the period was 1 hour, so they are in the in spiral phase, and let's say 1 kiloparsec away. That is very close. I mean, 1 kiloparsec may sound very large, but it is actually not too large in astronomy. And still, you can see that even then the strain is 10 to the minus 21. And if you take like really two neutron stars, like 1.4, yeah, even one solar mass is too smaller than neutron star. These are like basically test cases. This could be, you can take let's say white dwarf and see how much would be the emission. White dwarf period could be 1 hour, and this is the main source of noise for LISA. Anyway, so here, suppose you take a merger which happens in 10 milliseconds, let's say, and it is 1 megaparsec away, then also you can get 10 to the minus 22. So these are sort of order of magnitude estimates to see how much you can expect from these mergers. So, okay, now coming back to, okay, I'll first show the video and then we'll come back to those questions. So this is basically an animation, I hope you can see it, to show what is happening. You see that as time progresses, the frequency is reducing, that is the wavelength is, frequency is increasing, the wavelength is reducing. You see that wavelength is becoming shorter and shorter. And also you see that amplitude is increasing with time. This happens also for the bird's chirps sound. And that's why these are often called the chirp signal. And so this is basically what I have already described. And you saw that some energy, some waves left the system. Now there was a question that if gravitational waves weak, so in basically the question was from this sort of misconception that the energy, the gravitational waves are coming out of black holes. That is not true. Gravitational waves are actually not coming out of black holes. Gravitational waves are actually coming from the whole system. Nothing can come out of black hole. Black holes are event horizons. I mean, basically black holes are surfaces from which no information can come out. So nothing is coming out of the black holes. It is when the black holes are going around, the binding energy of the system is being radiated as gravitational waves. Okay, now there are more questions. So let me see. So I will come to the other questions later on. Okay, let me see if there is anything. There is a this question is good, that there is a is there a connection between the object's mass and the gravitational wave it produces? Yes, there is. So you can already see from this formula here that it sort of goes as m to the power 5/3. M is, let's say, the total mass of the system. Now, what happens is that the merger happens when these black holes touch each other or compact objects touch each other. So now if the black hole is big, then they touch early. Now if you do some mathematics, you will see that black hole's mass radius is actually proportional to its mass. It is not like normal objects where the mass goes as r cube when the density is fixed. Actually, black hole's density reduces as it becomes bigger and bigger, average density. So therefore, when the black holes are bigger, they actually merge at a much lower, at a higher distance, so much lower frequency. That is why the supermassive black holes cannot be detected by LIGO. LIGO can only detect stellar mass black holes, which are smaller and goes to a higher frequency. But on the other hand, more the mass, higher the energy emission, even though the frequency is lower. Okay. Are there destructive effects of gravitational waves in the vicinity of? Yeah, well, yes, possible that it can, the gravitational waves in the vicinity can trigger. So because the energy is very large, even though the coupling is smaller, it can trigger some perturbations in nearby astronomical systems, but we don't yet have any idea whether in practice we will be able to realize it or measure it. So the question is that another question is that the mass of 3 solar masses converted to energy come from black holes? No, it does not. It does not come from the inside of the black hole. It comes from the whole system together. It is like a proton electron system, right? Or you can take any other this kind of system, that their rest masses are still the same, but when they are bound, the total energy is still different. It is not exactly the sum of the rest masses of all the particles. It is similar to that. Okay, so there are more complicated situations which can arise. So one of the questions is that what happens to the whole process of merging and gravitational wave production with one of the stars in a binary says much larger than the other, say red giant, and the neutron star. The neutron star will accrete from the red giant, but the distance at that point when it is accreting is quite large. So the frequency, the period of this thing will not be in a range where the gravitational wave emission will be very large. Unless it happens too close, I don't think we will ever be able to detect it. It is like the Hall scalar binary pulsars, that we cannot detect the gravitational waves coming out of it, but we can see that because of the gravitational wave emission, there is a small change in its path. But when there is accretion, the orbit will be dominated, orbital distortions will be dominated by the accretion process rather than gravitational waves, because gravitational waves will not have much effect, I think. Okay, so can't we have many system in coalescence? That is a very interesting question. Yes. So we don't yet understand. There are many open questions, and we don't yet understand how the gravitational waves, these binaries, are actually produced and they evolve. One of the possibilities that people suggest is that there are three body interactions which actually trigger this process. Okay. Otherwise, a process could take longer time, but then it is triggered by this third mass, and one of them will be kicked out, and so on. So these are very interesting aspects which people are looking at. Okay, so I think there are too many questions coming now, and I cannot read. So I would finish the talk now in 5 minutes, and then we will come back to direct questions by hand raising. Okay, so now let me go back to. Okay, so somebody said my mic does not work. What triggers in spiral? Okay, I'll just answer that, and then I'll come to this. So nothing is triggering the in spiral. What is happening is that, suppose there is nothing in space other than two objects which are moving in some direction, but there will be still some gravitational interaction between them, right? There cannot be, there is nothing like no force on any of them. So because of the gravitational force, they will slowly start coming together. If there was no gravitational waves, of course they will stay at the same distance and go around each other, but because of the gravitational wave emission, they will start coming closer and finally they will merge. So this is like a natural process for any two binary objects to finally merge. That is their destiny, I think. Okay, so now coming back to this. So I will now finish this and then come back to more and more questions. Okay. So I talked about the compact binary coalescences, which is the primary source. But generally, if you solve this equation where, I told you that if you put the right hand side to be 0, then you get this kind of solution. But if you retain it and then solve for it, what you get in certain limits is the quadruple formula. And that basically tells us that the emission of gravitational waves from such a bound system is basically proportional to the second derivative. The strain is proportional to the second derivative of the mass quadruple moment. This Ij is basically an integral over okay, maybe I should write it here. Wait. Okay, anyway, I think you know multiple expansions. Actually, many of you have done multiple expansion. It's basically that. It is an integral, volume integral with, let's say, xi and xj are the two coordinates, that is the ith coordinate and the jth coordinate. I and j could be same also. I goes from 1 to 3, j goes from 1 to 3, and then there is a rho, which is the density. That is the mass quadruple formula, and then it is the second derivative of that. That basically gives you a general formula, even though in practice you have to use more accurate ones. Another way to look at it is basically the strain produced by gravitational waves is sort of the order of the non-spherical part of kinetic energy. So if you imagine that there is a system, a spherical system, a sphere, let's say, or a cylinder, and you take the symmetry axis to be the spin axis, and let's say a sphere, a cylinder is spinning. Now, if you calculate the mass quadruple of this cylinder, you will see that it is constant. It's not changing with time because it is symmetry. However, instead of the symmetry axis like that, if you take the cylinder like this and take the axis from here, then it is no longer going to be true. So if this pencil rotates like this, it is going to emit gravitational waves. But if it spins like this, it is not going to emit any gravitational waves. So based on that, there are many basically sources of gravitational waves which we can, which are potential sources, but we have not detected them. Essentially, anything that moves asymmetrically can produce gravitational waves. Like when I'm waving my hand, I'm producing gravitational waves, but they are very weak. Among the astrophysical sources, the short duration ones are the compact binary coalescence, which I have talked about. Supernovae could be one of those sources. There are a lot of numerical modelings going on to see. Gamma ray bursts are probably connected to compact binary coalescence, but there could be other sort of violent phenomena. Now, these are short duration sources, but there are long duration sources like continuous waves. So let's say that a pulsar, you have probably heard about neutron stars in these lectures. If a neutron star, which is spinning, let's say millisecond pulsar, has a small bump, let's say a small mountain on its surface, then it is going to emit a lot of gravitational waves. Whether the neutron stars have so much of asymmetry, mass asymmetry or not, is the research problem. Then there are magnetars, where the energy asymmetry comes from the strong magnetic fields. There are many sources. I will talk about. Okay, so let's say that there are supermassive black holes. Two supermassive black holes are going around each other. Since they are for a long time before they touch, they can basically, in a very stable frequency. So frequency will change very, very slowly. So that can be taken as a continuous source with a small variation in frequency. Certainly, it's true for smaller black holes going around a supermassive black hole, which are called extreme mass ratio in spirals, where the merger may happen after a very long time, but a kind of continuous signal will be coming from it. And then finally, there are stochastic sources. I already told you about one, that there are these early universe effects which may generate some kind of random fluctuations like the CMB, which are sort of these are called stochastic sources. But there is another one. Before we go to so early universe, there can be a collection of all the above sources like compact binary coalescence, pulsars, etc., all together in, let's say, some cluster of galaxy. There we would not know which source is emitting when, but we would know that there can be a bright spot in the universe in gravitational waves. This will be more like normal electromagnetic astronomy, where we see bright sources like a galaxy. When we don't know which star is where, but it's a stochastic source. And I already told you that most of the electromagnetic sources are stochastic. So, and in gravitational waves, also it is possible, even though the compact binary coalescences are where we can trace the phase. So this is sort of like a schematic that the sources basically span a large frequency band. Right now, we have only detected sources in the LIGO band near 100 Hz, where we have seen neutron star, and black hole coalescence so far. There may be, at some point, we may be able to see the supernova at higher frequencies. If there is a space-based detector, we may be able to see different kinds of sources. For space-based detectors, the background, this white dwarf binaries which are going around each other, there is a large number of them, and they can be a primary source of noise. We have not discussed noise yet, but we'll come to those later on. And there are many other sources. The supermassive black holes will come in LISA. I have already told you about. Okay, so I think I will stop here today, and the next lecture will be on detectors. Okay, I think I have covered everything about the sources. Let me see if there are any questions remaining. And now you can ask questions also by raising your hand in Zoom. You can. Okay, there is already a question. So go ahead.
Good morning, sir.
Yeah.
Sir, I have asked you the question about how can we differentiate between the Card black hole and Schwarzschild black hole by gravitational waves.
Correct. I forgot to answer that. I'll come to that.
Okay.
Yeah. Okay. So okay. After you are done, you mute yourself. I will not mute so that you cannot. So if I mute, then you would not be able to unmute. So if you mute, then you will be able to unmute and ask if there is if your question is not yet answered. So what happens is that I will go back to the slides a bit. Maybe you can see here. You see that this is a numerical simulation where there is a certain waveform here. Okay. This waveform depends on several parameters. The masses, primarily the masses and the spins of these components. Okay. If one of them is a Schwarzschild black hole, then certainly that is the spin is 0. The signal due to that object would be different if it was spinning. The signal you just saw here would have a certain modulation if one of the object is spinning. Therefore, by looking at this signal, the base signal that matches the data, we can figure out the spins of the individual object. Actually, we cannot completely do that, but we do it partly. At least we can get the projection of the spins along the angular momentum. But eventually, we may be able to get the full spin with we may be able to trace the full precision of this binary system. So what we can do then is we can identify whether an object has spin or not. That will distinguish between Kerr and Schwarzschild. Also, in the about the final black hole, if two of these objects have opposite spins, then it can cancel out. Okay. I hope you have answered your question. Okay, now the next one, Junik.
Hello, sir. Good afternoon.
Yeah, good afternoon. Oh, I unmuted you.
Yeah, sorry, sir. Sir, actually, the point is a part of my question you have already answered. There is an interaction between dark matter and gravitational waves. Sir, actually, there was a second part of the question, that is, does dark matter able to generate or produce gravitational waves?
Yes, yes, possible. So that is another research area. Now, so you know that we cannot confidently say that we know the origin of these black holes. One possibility is that some of these black holes are produced in the early universe. They are called primordial black holes. The primordial black holes could also constitute a certain component of the dark matter. There are some upper limits, but it is not yet clear that. We don't yet know that what fraction would be that, or there is zero component or not. So that is one channel. Second channel is that there can be clumps of dark matter. See, dark matter does interact through gravity, right? So if there are smaller clumps of dark matter in the galaxy or wherever, then there is a chance that two of them will come close and go around each other, or one of them can go around a black hole. So those possibilities are all there. Okay. Okay, once your question is answered, then you lower your hand so that we know that it's done. Okay. Yeah. Anusha.
Good morning, sir. So my question is, does the expansion of universe have an effect on gravitational waves?
Yes, it does. So just like for electromagnetic waves, the expansion causes redshift. For gravitational waves, also the expansion does cause redshift. So when we start detecting high redshift objects, we do have to account for uh, the redshift more carefully. In fact, another thing is that the early universe stochastic background that I was talking about have redshifted to a much lower frequency now. After they, okay, so at some point they entered the horizon and then they became frozen. I mean, they expanded. They started expanding with the universe. Okay. Any other questions? We have. Okay. Okay. So there are more questions on the chat box, so I can take those questions. Sorry, I will also see if there are questions on YouTube live. There are many questions, so okay, so I will answer few of those. Let me just get back to this one. One question is that could galactic mergers create gravitational waves? Of course they can. They can be a very big source of gravitational waves. However, the probability of finding a merger in our galaxy is very low. So that is why, I mean, like any other galaxies producing gravitation, the mergers which are happening in some galaxy. It can happen also in our galaxy, but the probability is very low. Okay, then okay, I'll just go to the YouTube live ones. Let me see which one to. Do higher order harmonics exist in gravitational wave synchrony? Yes, it does. I think there was a lecture by Professor Anand Sengupta on this. A detailed lecture is there on YouTube live of the LIGO India channel. Basically, what it means is that if you have, since the leading order in gravitational wave emission is quadruple, you see that let's say two objects are going around each other, and here is one configuration. Let's say I put the configuration like this, so that you can see only one of my fist, and now turn around and do like this. Okay, now if my fists were perfect spheres, then you would not be able to distinguish between this and that, right? So the fundamental mode in gravitational wave emission is twice the frequency, merger frequency, the frequency of the in spiral. However, if these objects were not so symmetric, so if the masses of these objects are close and both are, let's say, black holes, then clearly you can, it will be very difficult to distinguish. But if this difference become much larger, that is the mass ratio increases, then you would be able to start seeing higher harmonic effects in the signal. It will be third order onwards. Is there gravitational spectrum like electromagnetic spectrum? Yes, it is. It's for any object. In fact, any merger, the frequency sort of changes. So you can take the signal and do a Fourier transform of that, and you can get a spectrum. Okay, somebody I see that has already. Okay, the dark matter question I have already answered. Let me see. Can we try to detect gravitational waves from dark matter? Yeah, I have answered that. There is a lot of effort going on along that direction in two ways. One, through lensing, other by checking whether dark matters themselves can generate gravitational waves. Okay, so one question is that the signal duration depends on the source. It was visible for about 0.2 seconds for the first black hole merger, with whether 100 seconds for the neutron star merger. Okay, so this is basically because of the fact that the black holes touch too early. But since the neutron stars are much smaller, let's say that their radius would be 10 kilometers, Then what? But on the other hand, the black hole's radius would be the first one which you are observed were like 100 kilometers. So the neutron stars could go around each other for a much longer time. But the thing is that they emit lesser energy. So both of them were detected with the same, what is called the signal to noise ratio, similar signal to noise ratio. The neutron star merger lasted for a longer time with smaller signal. The black hole lasted for a smaller time with a larger signal. Okay. Where did my... Let me see. Okay, there are no more hands up, but there are questions here I can see. Okay, so the question here is that to detect the redshift of gravitational wave, we should have a standard spectrum that we... I will come to this question that how exactly we measure redshift with gravitational wave tomorrow. Another question is that, like for EM wave, the detector antenna needs to be of similar size as the wavelength. Is there any similar need for gravitational waves? I will come to that in the last lecture, or maybe tomorrow. Yeah. It depends on the design, of course. It does not have to match exactly, but yeah, it effectively becomes similar. So another interesting question, that the fact that Andromeda galaxy is getting closer to Milky Way, does it produce any significant gravitational wave? It does produce the gravitational waves, but the thing is that the frequency is too low. The frequency would be, I think, of the order of, the period would be of the order of like maybe 10 billion years or so, which would mean a very, very small frequency. So it will be very difficult to observe it. There are low frequency signals which we can observe now, but they were high frequency at some point, and that CMB basically represent that. Okay, I think I will take the last question because we are already 20 minutes past the deadline. Can we trace the trajectory of a gravitational wave like it has less? Exactly. So the trajectory of gravitational waves are exactly the same as electromagnetic waves, but electromagnetic waves can get much more, can interact much more and deviate because of those interactions. But gravitational waves interact very weakly, so they don't. They maintain the path. Okay, I think I will stop here, and again see you tomorrow at